Okay, so let's look at the first section that we're looking at in part 2, which is affine word forms and index evolution. So we now lift the single-step row calculus to sequences of tokens, what we call words. We show that any admissible word W induces a strictly affine map on the internal index M. And we derive the exact recurrence relation that governs the evolution of MT along the trajectory. So you could say the trajectory T, right? So the affine word form. So let W be T1, T2, all the way to Tn, be a sequence of n tokens where the tth token uses the column lift PT. So a word need not use a single P lift. So P can vary throughout the word. So let alpha, beta, CT, alpha T, BT, CT, and delta T be the parameters of the rows selected at step T. So we'll recall the single step update from above, where xt is equal to 6 times 2 raised to alpha t plus 6 pt times mt minus 1, so it's always the previous t, and xt is the output here, plus kt, which is the constant part. So it is kt is beta times 64 raised to p plus c over 9, and then plus delta t. So this is the tth output. M is the t minus 1 index, where ktp is, as we said, beta t times 64 raised to pt plus ct over 9. By composing these linear maps, the action of the entire word W on the internal index M0, which is M of the initial X that starts off the word. So if it was, for example, here T1, T2 up to Tn, M0 is M based on T1. Takes a unified affine form. So let's look at the affine word form. For any admissible word W of length n, there exists constants AW greater than 0 and BW, an integer, such that the terminal value xn is given by xw of m0 equals 6 times AW m0 plus BW plus delta W, where AW is given by the product of 2 times AT plus 6 PT. So this is the same as 2 raised to the sum of AT plus 6 PT, which here we call 2 raised to AW for the word, where AW is defined as the sum of AT plus 6 pt from t equals 1 to n. BW is an integer constant, so BW here is an integer constant determined by the sequence of accumulated shifts, and delta W is the offset delta of the last token Tn. Okay, so the proof is by induction on n. For n equals 1, the form matches the row definition with AW equal to 2 raised to alpha plus 6p and BW equals KP. For the inductive step, assume xn minus 1 equals 6 open bracket times an minus 1 m naught plus bn minus 1 close brackets plus delta n minus 1. The next index is mn minus 1 equals the floor of xn minus 1 over 18. Substituting this into the linear form for step n preserves the affine structure. So in index evolution, which is coming up next, we have the exact coefficients of such a system. Okay, so let's look at index evolution and the router. So the nonlinearity of the Collatz map enters solely through the floor function mt equals the floor of xt over 18. We can resolve this floor exactly by tracking the router remainders. So proposition 2, the index recurrence. So this is what was referred to earlier. Let AT be equal to 2 raised to alpha t plus 6 pt be the slope of step t. The internal index evolves according to mt equals at, which is defined here, mt minus 1 plus kt of p minus jt all over 3. So where jt is equal to at mt minus 1 plus ktp mod 3, so jt is equal to all this, is the router index required for the next step to be admissible. So let's prove this. So recall that xt is equal to 6 times at mt minus 1 plus kt plus all that in brackets plus delta t. So this is the whole definition of xt. This is derived from f of in this case ptmt, right? So and so this is just the same thing rewritten as a term in the term t of so therefore dividing by 18, because xt over 18, this here equals 6 open brackets at times mt minus 1 plus kt close brackets plus delta t all over 18. So if we cancel out the 6, because 18 is divisible by 6, we get at mt minus 1 plus kt all over 3 plus delta t over 18. So let n be at mt plus kt, so this numerator here. We can write n is equal to 3q plus r, where r is any of 0, 1, and 2. Then mt, so mt would be xt, the floor of xt over 18. mt is equal to the floor of xt over 18, as you see here, which equals, so taking n here being 3q plus r, and recalling that at mt minus 1 plus kt was divided by 3 here in the expression for xt over 18, we would get q, so the floor of q plus r over 3 plus delta t over 18. Since r is less than or equal to 2, so as you can see here, the maximum value for r is 2. And delta t is less than or equal to 5, since delta is either 1 or 5, so its maximum value is 5. The fractional part, r over 3 plus delta t over 18, is less than or equal to 2 over 3 plus 5 over 18, which is equal to 17 over 18, which is less than 1. Thus the floor is exactly q. Solving, n equals 3 times mt plus r. So because q is empty, we can write it as mt. Mt was equal to this, and mt is equal to q. So we can write n equals 3q plus r to 3 times mt plus r. For mt, so writing this, for mt yields mt equals open bracket n, capital N minus r, close brackets, all over 3. In our notation, the remainder r is exactly the router index jt for the subsequent step. Yeah, and we, in this remark, we go on to justify why why r is jt. So, oh, sorry, not in this remark. That's in a remark you'll find in the paper, because it's not included here, but it's included in the paper. In this remark, we're looking at the closed form for the index update and the router remainder. In the proof of proposition, the index recurrence, which is this proposition, we set n to be defined by at mt minus 1 plus kt, where at is 2 raised to, so let's just look at it. So at is 2 raised to alpha t plus 6 pt, right? So here we know n is defined this way, at mt minus 1 plus kt, so that n is equal to 3q plus r, and r is any one of 0, 1, or 2. By Euclidean division, the quotient is q is equal to the floor of n over 3. And we identify this quotient with the next index mt, as we showed above. That means mt equals q. Writing the remainder as the router output, jt is defined as n mod 3, which is any one of 0, 1, and 2. We obtain the floor-free index recurrence. So mt is equal to, so this is without using the floor, mt is equal to n minus jt over 3, which is equal to at mt minus 1 plus kt minus jt all over 3. In our parameterization, at is equal to 2 raised to alpha t plus 6 pt. Kt is equal to beta t times 2 raised to 6 pt plus ct all over 9, which is the same as bt times 64 raised to pt plus ct all over 9. So equivalently, mt is equal to this massive expression here, which is 9 times, so we're making 2 raised to alpha t plus 6pt times mt minus 1 minus jt kind of fit into this tail here, so plus beta t times 64 raised to pt plus ct all over 27. Or we could also rewrite it in the same way as we had before, where 2 raised to alpha t plus 6pt mt minus 1 minus jt all over 3 plus then beta t 64 raised to pt plus ct over 27, which we may define as gt pt. Here gt pt equals this part, so all of this here, which is equal to, which is the same as beta t times 64 raised to p plus ct all over 27 collects the p dependence of the affine offset. So while the router remainder jt is chosen so that at mt minus 1 plus kt minus jt is divisible by 3. Right, so end of remark there. So writing mt in this form is very cumbersome, but we'll see kind of cheaper ways to get at mt and jt later on. So here's another remark: index update and complementary 1/3 fractions router. Let's look at it. Okay, let's look at index update and complementary 1/3 fractions of the router. So fix a step t and let n be defined as at mt minus 1 plus kt pt, an integer, and jt is defined as n mod 3, any one of 0, 1, and 2. So jt being any one of 0, 1, and 2, then n is equal to 3 mt plus jt. Hence, mt equals the floor of n over 3, which is equal to n minus jt over 3, which is equal to at mt minus 1 plus kt pt minus jt over 3. In our parameterization, at is 2 raised to at plus 6 pt, and kt is beta t times 64 raised to pt plus ct all over 9. So one may also write in the split form, which we've seen before, mt equals at mt minus 1 minus jt all over 3 plus kt pt over 3. Although kt pt over 3 need not be an integer, it is complementary to the first term, since jt is congruent to at mt minus 1 plus kt pt mod 3, we have at mt minus 1 minus jt is congruent to negative kt pt mod 3. So the two summands are always carry opposite 0, 1/3 or 2/3 fractional parts, and therefore their sum mt is an integer. So complementary 1/3 fractions and a convenient choice of h. So let n be defined as at mt minus 1 plus kt pt, an integer, and jt is defined as n mod 3, any one of 0, 1, and 2, so that n equals 3mt plus jt, and therefore mt equals at mt minus 1 plus kt pt minus jt all over 3, an integer. Define ht as at mt minus 1 over 3, which is equal to at mt minus 1 mod 3 over 3, which is any one of 0, 1/3, and 2/3, so that at mt minus 1 over 3 minus ht is an integer. So writing mt equals at mt minus 1 over 3 plus kt pt minus jt over 3, and using mt, an integer, we obtain the complementary integrality relation kt pt minus jt over 3 plus ht is an integer. Equivalently, the 2 over 3 terms have opposite fractional parts. So at mt minus 1 over 3 is congruent to negative kt pt minus jt over 3 mod 1. Okay. Let's look at the closed form for mn. So unrolling the recurrence yields a summation that describes the trajectory's history. So this theorem, index evolution formula, for a word of length n, the final index mn is related to the start m0 by mn is equal to aw m0 over 3 raised to n plus the summation from t equals 1 to n of a term pnt over 3 raised to n minus t plus 1 times, open bracket, ktp minus jt, close brackets, where pnt is equal to the product of from I equals t plus 1 to n of ai, is the product of slopes from step t plus 1 to n. Right? So, and here's a remark: zero stat independence. If we start from x naught equals 1, or any minimal element where m naught equals 0, the first term vanishes, right? This vanishes because m naught is 0. The entire trajectory is then determined solely by the structural constants of the word, the k values, and the routing choices j. This confirms that the path from 1 is deterministic and algebraically fixed. Right? So since you can discard this first element here, and so the dependence on the AWs and so on and 3, that all goes away. Then you just have a summation like this. Okay, let's look at steering and monotone padding, the next section. So, steering and monotone padding. The core of the in-bus calculus is the ability to manipulate the affine parameters of a word to satisfy specific modular congruences. We achieve this via padding, appending short sequences of tokens to the end of a word. So let's look at steering gadgets. There's a definition. Steering gadget. A steering gadget is a short admissible word S that begins and ends in the same family F, which is either E or O. Appending S to a prefix W ending in F preserves the terminal family but modifies the affine parameters. So using slope boost, it multiplies the slope AW by 2 raised to delta V2, strictly increasing the two-adic valuation, and intercept control. It modifies the intercept BW modulo 2 and modulo 3. Because these gadgets preserve the terminal family, they allow us to steer the values of A and B without altering the routing requirements for any subsequent steps. So then, here's a finite steering menu. We fix a finite set of canonical gadgets SP for each column P greater than or equal to 0. These are sufficient to generate any required two-adic lift and parity. So here's a table with the canonical steering gadgets. So here's family block type path, the effect on the valuation of A, the change in valuation, so delta valuation of A, and the effect on B, which is the second part of the affine formula. Okay, so the remark: higher columns. For P greater than or equal to 1, the structure remains identical, but the valuation lift increases by 6P per token. The parity effects depend on KP mod 2, which is tabulated in the full reference implementation. The menu above is sufficient for P equals 0. So there's a reference implementation in the appendices, so you find it there. So mod 3 steering. In addition to parity, we must often control B mod 3 to ensure the final congruence is solvable, removing factors of 3. So here is a lemma, mod 3 control. For each family F, being either E or O, the affine maps B to 2 raised to alpha times B plus K mod 3, induced by the available tokens, generate the full affine group. So this is the one-dimensional affine group on F3. Consequently, from any current state BW, there exists a steering gadget of length less than or equal to 2 that sets the new intercept B prime congruent to R mod 3 for any target, R being any of 0, 1, and 2. So here's a proof. In family O, omega 1, capital omega 1, maps B to 2B plus 1, and capital omega 0 maps B to 2B plus 2. These two operations generate all permutations 0, 1, and 2. In family E, capital psi 0 maps B to B, identity, and psi 2 maps B to B plus 1, shift. Iterating capital psi 2 reaches any residue. Okay, let's look at the monotone padding lemma. We combine these results into the primary tool used for inductive lifting. Lemma 6, monotone padding. Okay, so monotone padding. Let W be any admissible word ending in family F, where F is O and E, O or E. For any target valuation K and any target parity B, which is either 0 or 1, there exists a padding string S such that the extended word W prime, which is equal to W dot S, satisfies family preservation. So W prime ends in the same family, F. Valuation target, so the two-adic valuation of AW prime is greater than or equal to K, and parity control BW prime is congruent to B mod 2, right? So any target parity B, so this is where this B comes from. So proof, since every gadget in table 4 has delta V2 greater than 0, we can repeat the preserves parity gadgets to raise the valuation of A arbitrarily high. That's a monotone lift. Monotone because the changes go in just one direction, upward, greater and greater. If the resulting B has the wrong parity, we append exactly one toggle parity gadget, for example, capital omega 2 or small psi 2 followed by or composed with small omega 1. This flips the bit B mod 2 and adds positive valuation satisfying all conditions. Okay, so joint mod 2, mod 3 steering with monotone padding. Fix a family F being either E or O, and let W be any admissible word ending in F. Let K be greater than or equal to 1, and let R be any of 0, 1, 2, 3, 4, and 5, be any target residue class. Then there exists an admissible extension S, such that the extended word W prime equals W and WS and satisfies family preservation. W prime ends in the same family. Valuation target, the valuation of AW prime is greater than or equal to K, and joint steering. So BW prime is equal to R mod 6. Moreover, S can be chosen from a bounded length concatenation of the canonical gadgets in table 4. So, proof of that. Step 1, raise the valuation, two-adic valuation of A without leaving the family by lemma 6, which was the previous lemma, for any prescribed parity class B either 0 or 1, there exists an admissible padding word PB such that W1 is defined as W.P6, ends in the same family, and satisfies the two-adic valuation of AW1 greater than or equal to K, and has BW congruent to B mod 2. In particular, after this step, we have achieved the valuation target and fixed B mod 2. So step 2, finite controllability on B mod 6 inside a fixed family. Consider the finite directed graph whose vertices are the residue classes F and B bar, which are either E or 0 cross the integers mod 6, and whose directed edges are induced by appending one canonical gadget from table 4, i.e. FB to FB prime bar, if appending that gadget is admissible from family F, and maps B to B prime modulo 6 according to the paper's token update rules. Because the gadget set is finite and the state space has size 12, this is a finite graph. In fact, we draw this graph later on in analysis. By the mod 3 control lemma, lemma 5, within each family F, the available steering moves act transitively on B mod 3. Table 4 also contains at least one parity preserving gadget, effect B congruent to B prime mod 2. Let me not obscure this. And at least one parity toggling gadget, effect B prime congruent to B plus 1 mod 2 within each family. Consequently, the induced moveset is transitive on B mod 6 within each family from any B bar, which is the integers mod 6. One can reach any other R bar, which is also mod 6, by a word of bounded length, bounded by the diameter of this finite graph. So let Q be such a steering word, a concatenation of canonical gadgets that sends BW1 mod 6 to the desired R mod 6 while remaining in family F. Set W prime, defined by, let me not obscure this, W1.Q. Since all gadgets in Q are admissible and family preserving, W prime ends in family F. Since the two-adic valuation of A is non-decreasing under the padding / steering gadgets used in the paper, as recorded in table 4, we still have the two-adic valuation of AW prime is greater than or equal to K. Finally, by construction, BW prime is congruent to R mod 6. The bounded length claim follows because the steering word length can be chosen less than or equal to 11 by finiteness of a 12-state directed graph, and in practice is much smaller. One can tabulate the shortest paths. And that ends the proof there. Okay, let's move on to routing compatibility. So, as routing compatibility, a central challenge in the inverse calculus is that the router JT which is the floor of xt over 6 mod 3, depends on the floor of the current value. Floor, right? If we adjust the initial input m to satisfy a condition at step n, we risk changing a router at step t less than n, which would invalidate the chosen row sequence, so-called branch flip, a branch flip. We now prove that this can be prevented by imposing a sufficient two-adic constraint on M. Okay, so let's look at that. The stability threshold. Let W, which is a word, be T1, T2, all the way to Tn, be a fixed prefix. Let AT denote the cumulative slope up to step T. So AT here is the product of 2 raised to alpha, the product from from 1 to T of 2 raised to alpha I plus 6 pi, which we can call 2 raised to st, where st is the sum from I equals 1 to t of alpha I plus 6 pi. Right? So the value xt depends on m via the term atm. Right, so in the normal affine form, this is ATM is the first term. We stabilize the flow functions. To stabilize the flow functions, we must control the lower bits of M. So, definition, stability threshold. The stability threshold, S star, for a word W is the maximum accumulated exponent along the path plus 1. So here S star is defined as 1 plus max st, here's st, and this is from for t greater than or equal to 0 but less than n, right? So it's 1 plus that max. That's what we call the stability threshold as S star. Okay, so let's look at the compatibility lemma. So lemma 8, routing compatibility. Let W be a fixed admissible prefix with planned routers Ji to all the way to Jn, J1 to Jn. If we restrict the input index M to a specific congruence class, so M here congruent to M star mod 2 raised to S star. So S star here is the stability threshold. But here we're just saying if we restrict the input index M to a specific congruence class, right? So here M is congruent to some M star mod 2 raised to S star, where M star is compatible with the entry family. Then the router remainders RT plus 1 computed along the trajectory are invariant for all M in that class. Specifically, if M star generates the correct routers, then every M congruent to M star mod 2 raised to S star generates the same routers. So what's the proof? So let's look at the proof, right? Recall the index recurrence, right? So we had shown this, MT equals all this. So MT equals AT, right? And I think AT is AT is described here, which is the product from I equals 1 to t of 2 raised to alpha I plus 6pi. So here's mt, so that's ATM plus BT minus RT plus 1 all over 3, that's MT. This expression has been shown before. The router RT plus 1, which is this here, is determined by ATM plus BT mod 3, right? Which we've also worked on this before and explained why. Since AT is equal to 2 raised to ST is co-prime to 3, fixing M mod 3 fixes the router sequence modulo 3. However, we must also ensure the integrality of the division, the flow. If we fix M mod 2 raised to S star, we fix the lower S star bits of M, since ST is less than S star. The term AT times M is congruent to AT times M star mod 2 raised to S star plus ST. The division by 3, multiplication by the inverse of 3, which is, as you can see, we divide by 3. In the division by 3 in the two-adic integers preserves this two-adic precision. Thus, the decisions made by the flow function, which depend on lower bits, remain constant. So, well, when you get the paper, it might be worth going through this slowly. But there's more interesting stuff towards the the end of this section. So let's get through it. So next, let's look at application, freezing the prefix. This is an application of what we've been looking at so far. Okay, so let's look at the application. This lemma provides a modular locking mechanism. So, freezing the prefix. Let's look at it. Construct a prefix. Choose a word W to reach a specific family or intermediate value. Calculate S star. Sum the exponents. Restrict M. Solve the linear congruences for the routers modulo 3 and then lift to modulo 2 raised to S star. Once M is restricted to this class, we can append any number of steering gadgets to the end of W, as long as the final choice of M respects the constraints M congruent to M star mod 2 raised to S star. Let me not obscure this. The prefix W will execute exactly as planned with no branch flips. And that is the end of part 2. So now we start part 3. I call this the most interesting part of the paper. We'll look at some more generalizations, but towards the end of part 3, we'll use the tools that we have built so far to prove some very definitive and consequential lemmas and theorems. Right, so let's jump right in. We'll start with residue targeting via last row congruence.